Hello everyone, welcome to my lecture. Here we will be discussing about linearly independent and dependent vectors, or linear independence and linear dependence. So here you can see the definition. Let V be a vector space over F, or a field F. A subset S equal to alpha 1, alpha 2, alpha 3, etc. up to alpha n of V is said to be linearly dependent if there exists scalars C1, C2, C3, etc. up to Cn in F, not all of which are 0, such that C1 alpha 1 plus, C2 alpha 2 plus, C3 alpha 3 plus, etc. up to Cn alpha n equal to 0. Otherwise, it is known as linearly independent. That means, suppose you have a vector space V over a field F. Vector space, regarding vector space, we have discussed in one of your previous videos. Okay, if you have any doubt, you can check that videos. Yes, suppose you have a vector space V over a field F, and you have a subset of that V. You have a subset S of that vector space V. Okay, these are the elements of that S: alpha 1, alpha 2, alpha 3, etc. up to alpha n. Then when can we say that this subset S is linearly dependent? Or when can we say that these vectors alpha 1, alpha 2, alpha 3, etc. to alpha n as linearly dependent? When can we say that? If it satisfies these conditions. Okay, what are those conditions? If there exists scalars C1, C2, C3, etc. to Cn in our field F, and not all of which are 0. All of these C1, C2, C3, etc. to Cn should not be 0. One or two can be 0, but all of them should not be 0. Okay, such that it should satisfy this equation: C1 alpha 1 plus, C2 alpha 2 plus, C3 alpha 3 plus, etc. up to Cn alpha n equal to 0. Then we can say that these vectors alpha 1, alpha 2, alpha 3, etc. to alpha n, or this subset S of this V, is linearly dependent. Otherwise, it is known as linearly independent. That means you cannot find such C1, C2, C3, etc. to Cn, and all of which are not 0. If you are not able to find such C1, C2, C3, etc. to Cn, then we can say that they are linearly independent. That means this equation is happening: C1 alpha 1 plus, C2 alpha 2 plus, C3 alpha 3 plus, etc. up to Cn alpha n is 0 only if all of this C1, C2, C3, etc. up to Cn are 0. Only in that case this equation is happening. Then we can say that they are linearly independent. Okay, but if you have C1, C2, C3, etc. up to Cn which are not 0, all of them are not 0, some are not 0, but all of them are not 0, then we can say that they are linearly dependent. Okay, let's see some examples. Here you have one example for linear dependence. This is linearly dependent example, and this is an example for linearly independent. See, suppose you have P3 of x over R. P3 of x means set of all polynomials whose highest degree is 3. Okay, the degree is at most 3. Okay, so it includes all the polynomials whose degree is 3 and less than 3. Degree 2, degree 1, degree 0, all such polynomials are included here, but more than 3 is not allowed, at most 3. Okay, and here our field is R, set of all real numbers. And consider a subset of this polynomial set. Okay, subset of this P3 of x. Okay, s equal to 1 plus x, 2 plus 2x, 0. All these are elements of P3 of x because all of them are polynomials whose degree is less than or equal to 3. Okay, so all of them are elements of P3 of x. This is an example for linearly dependent vectors or linearly dependent set. Okay, I will show you how. First of all, you should understand what are the alpha 1, alpha 2, alpha 3, etc. up to alpha n here. These are elements of our S. Okay, so what are the elements of S here? 1 plus x, 2 plus 2x, and 0. Okay, so these are alpha 1, alpha 2, alpha. So you can take alpha 1 equal to 1 plus x, alpha 2 equal to 2 plus 2x, and alpha 3 equal to 0. Okay, now when can we say that these vectors alpha 1, alpha 2, alpha 3, or 1 plus x, 2 plus 2x, and 0, when can we say that they are linearly dependent? If there exists C1, C2, C3. Up to C3 is required because we have only up to alpha 3. Okay, so this C1, C2, C3, etc. up to Cn, you can stop up to C3. C1, C2, C3 is required, where it should be in our field R. Here R is our field. Okay, so you should find real numbers C1, C2, C3 such that this equation C1 alpha 1 plus C2 alpha 2 plus C3 alpha 3 plus etc. up to Cn alpha n equal to 0 is satisfied. Okay, and all of them are not 0. All of those C1, C2, C3 should not be 0. Okay, see, suppose you have C1, C2, C3 belongs to R, C1, C2, C3 belongs to R. Okay, then let's apply in this equation C1 alpha 1 plus C2 alpha 2 plus C3 alpha 3 etc. up to Cn alpha n equal to 0. C1 alpha 1 plus C2 alpha 2 plus C3 alpha 3 equal to 0. Okay, that means C1, what is alpha 1 here? 1 plus x. Alpha 1 is 1 plus x plus C2 alpha 2. What is alpha 2 here? 2 plus 2x. 2 plus 2x plus C3 into what is alpha 3? That is 0. C3 into 0 equal to 0. Okay, so can we say that this equation will happen, or this equation is satisfied only if all of those C1, C2, C3 are 0? Is it necessary that C1, C2, C3 must be 0 so that this equation is correct? No, this will happen if you have C1 is equal to 2 and C2 is equal to minus 1. Okay, if this will happen if C1 is equal to 2 and C2 equal to minus 1. See, if C1 is equal to 2, this becomes what? This becomes 2 into 1 plus x. Okay, 2 into 1 plus x. And if C2 is minus 1, this becomes what? This becomes minus 1 into 2 plus 2x. Okay, plus C3 into 0 is always 0. So equal to 0. This is correct only, right? So this becomes what? If you take this 2 inside, this becomes 2 plus 2x only. Okay, 2 plus 2x. And minus 1 into this one means that 2 plus 2x only. 0, you can ignore, equal to 0, right? This is correct only. Okay, so this equation is satisfied. This equation is satisfied when C1 is 2 and C2 is minus 1. Okay, that means all of those C1, C2, C3 are not necessarily 0. You can have this equation even without C1, C2, and C3, all of them equal to 0. Because here C1 is 2, C2 is minus 1. They are different from 0. All of them are not 0. Okay, so that is a condition for linearly dependence. Not all of which are 0. All of them are not 0 here. Okay, so here our C1 is what? C1 is 2 and C2 is minus 1. So it's not necessary that all of them are 0. No, it's not necessary. Even without all these values are not equal to 0, we can have this equation. Okay, so that is the definition of linearly dependent. Okay, so they are linearly dependent. Okay, these vectors 1 plus x, 2 plus 2x, 0, they are linearly dependent. Okay, so we can write they are linearly dependent. Okay, they are linearly dependent. Next, let's see one example for linearly independent vectors. Linearly independent. Suppose you have all 2 by 2 matrices over the field R. Okay, that means here our vector space V is what? Set of all 2 by 2 matrices. Okay, and our field is R. And we are taking S, a subset of this vector space as this. Okay, first element is the matrix 1 2 0 1, second one the matrix 1 1 0 1, and third one matrix 2 0 1 3. Okay, so what are our alpha 1, alpha 2, alpha 3 here? Only 3 elements here we have, so up to alpha 3 only we have. So this is alpha 1, so we can alpha 1 is equal to 1 2 0 1. This is alpha 2, alpha 2 equal to 1 1 0 1, and this is alpha 3 equal to 2 0 1, 3. Okay, these are our alpha 1, alpha 2, alpha 3. Now we can say that these vectors alpha 1, alpha 2, alpha 3 or this set is linearly dependent if you can find scalars in this R C1, C2, C3. Okay, such that this equation is satisfied without all of them equal to 0. Okay, if all of them are not equal to 0 and this equation is satisfied, then we can say that linearly dependent. Otherwise, they are linearly independent. That means this equation cannot happen if all of them are not equal to 0. That means this equation will happen only if all of them are 0. This equation will happen only if all these C1, C2, C3, etc. up to Cn are equal to 0. Then we can say that they are linearly independent. Okay. If at least one of them, okay, if at least one of them are not 0, like this case, here C1 and C2 are not 0, right? That's why they are linearly dependent. Okay. Yes. So for that, suppose we have C1, C2, C3 belongs to R. Okay. Now let's take C1 alpha 1 plus C2 alpha 2 plus C3 alpha 3 equal to 0. That means C1 into what is alpha 1? This is alpha 1, 1, 2, 0, 1. 1, 2, 0, 1 plus C2 alpha 2. What is alpha 2? 1, 1, 0, 1. 1, 1, 0, 1 plus C3 alpha 3. What is alpha 3? 2, 0, 1, 3. 2, 0, 1, 3 equal to 0. Okay, that means if you take C1 inside, C2 inside and C3 inside, so this becomes C1, 2C1, this is 0 only, this is also C1. Okay, so C1, 2C1, 0, C1 plus this becomes C2 into 1, C2, again C2 into 1, C2, C2 into 0, 0, C2 into 1 again, C2 plus this becomes C3 into 2, 2C3, C3 into 0, 0, C3 into 1, C3 and C3 into 3, 3, C3 equal to 0. Now let's add them matrix addition C1 plus C2 plus 2C3 equal to, see here 0 means 0 vector only, sorry 0 matrix. Okay, 0 means 0 matrix only. This one can be written as 0 matrix. Okay, so C1 plus C2 plus 2C3 should be equal to 0. C1 plus C2 plus 2 C3 equal to 0. So equation number 1. Next, 2C1 plus C2 plus 0 equal to 0. 2C1 plus C2 plus 0 equal to 0. That is equation number 2. Next, 0 plus 0 plus C3 equal to 0. 0 plus 0 plus C3 equal to 0. That is equation number 3. And last one, C1 plus C2 plus 3 C3 equal to 0. C1 plus C2 plus 3 C3 equal to 0. Equation number 4. Okay. So from equation 3, we can directly take C3 equal to 0. Okay. C3 equal to 0, we can directly take from equation 3. Okay. C3 equal to 0. So here, if we substitute that value of C3 here, this equation becomes what? This equation becomes, this C3 becomes 0. See? So C1 plus C2 equal to 0. C1 plus C2 equal to 0. Okay. Suppose this is equation number 5. This is equation number 6. Next, 2C1 plus C2 plus 0 means 2C1 plus C2 only. 2C1 plus C2 equal to 0. Okay. Question number 7. And here also, in this equation, if we substitute the value of C3 we know that is 0. So that 0, if you substitute here, this also becomes 0. So C1 plus C2 equal to 0. Okay. C1 plus C2 equal to 0. Okay. That is same as our equation number 6. Yes, that is our equation number 6 only. Next, if you subtract this equation 7 minus equation 6, what you will get? Equation 7 minus equation 6. Let's do equation 7 minus equation 6. What will happen? See, C2 and minus C2 will get cancelled. 2C1 minus C1 becomes C1 only. So C1 equal to 0 minus 0, 0. So C1 is also equal to 0. C3 already we got 0. Okay. Now, if you put this value of C1 in equation number 6, what will happen to equation number 6? So this C1 becomes 0. So 0 plus C2 equal to 0. That means C2 is also equal to 0. Okay. Let's see what happened here. That equation, that means C1 alpha 1 plus C2 alpha 2 plus C3 alpha 3 equal to 0. This is happening only when C1 is equal to 0, C2 equal to 0, and C3 equal to 0. Only in this case that is happening. That means all of these values C1, C2, C3 are not 0. Okay. Okay. Then we can say, sorry, all of these values C1, C2, C3 are 0. All of these values C1, C2, C3 are 0. So they are linearly independent. Okay. Linearly dependent means what? Okay. Linearly dependent means, this is the definition of linear dependence. Okay. Linear dependent definition means all of which are not 0. Not all of which are 0. Okay. That's why here we got this first example as linear dependent. All are not 0. Okay. Only see here C1 is 2 and C2 is minus 1. C1 and C2 are different from 0. Okay. So it is possible to have the values C1 and C2 different from 0. That is possible. Okay. So all of them are not 0 here. So that's why linearly independent. Sorry, linearly dependent. Okay. Linearly dependent. But here in this example, see, all of them are 0. Okay. All of them are 0. So that's why it is linearly independent. Okay. Thanks for watching.